Okay, now for the rest of our lectures, we will basically apply Green's theorem. That's at the center of our discussions. Now, Green's theorem, recalling what it said, under certain circumstances, it connected a double integral to a line integral on the boundary of the region D. Okay, but more closely, let me say a remark. Okay. So in view of Green's theorem, okay, basically, if P and Q are not only continuous, but have continuous partials on, okay, but also and in the interior of, okay, the curve C of the, okay, region bounded by, okay, the curve C. So it is not enough that it has continuous partials on just on the curve or near the curve, but also inside the region bounded by the curve. So this is the extra part that Green's theorem emphasizes. Okay. Then, of course, we have okay, this closed C is 0. Namely, okay, by Green's theorem, this was double integral q sub x minus p sub y. Okay. And yes, of course, sorry. Then I should say here, if q sub x is p sub y, then, okay. Then we get this because this is 0, and we can apply the Green's theorem. So the point is that the functions p and q should have continuous partials as well in the inside of the region bounded by C. Then Green's theorem is applicable. Whenever we can apply it, this integral, the closed on closed C, is 0. This is true for all curves C, since true for all simple, okay, closed, piecewisely smooth C's. Okay, this says that PQ is conservative. So, the condition q sub x equal to p sub y implies conservativeness of PQ, for which we had a counterexample, where this condition was not satisfied if the partials are continuous inside the curve C as well. Okay. Now, one way of formulating this condition is the following. Is to say that D is a simply connected region. Okay. Well, this means exactly that any closed curve in D. Okay. This means that. Okay. Interior. Exactly that. Okay. If C is a curve in D, then it's then the region bounded by it let me give a name to this region, say R. Okay, also is also contained in D. So a simply connected region is a region so that whenever you take a closed curve in it, its inside part is also in D. Okay. Thus, okay, if PQ have continuous partials, okay, in D, and C is nice enough closed curve in D, then okay, Green's theorem is applicable. Okay, because the inside part is also in D, and because P and Q have continuous partials in D, they have continuous partials also inside the region bounded by C. Okay, so we get the following final formulation. Okay, the previous theorem modified. Okay. Now let D be an open, simply connected domain. PQ have continuous partials in D. Okay. Then the following are equivalent. Okay. A, the integral P dx plus Q dy is path independent. Well, we already stated this, so this is repetition. Okay. And this integral over simple, closed, and piecewisely smooth curves lying inside D, you have zeros. Finally, which was the third condition that we already proved to be equivalent, this is conservative. And now we can add equivalently that Q sub x is equal to P sub y on D. So we already had shown equivalence of the first three, and that C implies D as well. So the only missing part was D implies any of these. Well, it is because we have a simply connected domain and Green's theorem. Since now, okay, D being simply connected, okay, Green's theorem is applicable. And, okay, D implies any of these three because they are equivalent, but in particular, this implies B or A or C. Okay. So this is the proving question. Well, before we apply these results to our examples, let us note the following figures, namely what are simply connected in fact. Well, for example, a circle, it should be open, okay? Or even if the figure is a little bit distorted, okay? These are simply connected. Okay. But, for example, okay, even if you have a nice circle, okay, but some part of it is taken away. Okay. This is not simply connected. Because, okay, as we already did in the example, if you draw a closed curve somewhere here, it's okay, inside is here. But if you draw a closed curve so that the inside contains this small circle, okay, which is not inside D, okay, this fails to be not simply connected. Or, for example, if you have such a, okay, curve, I did not emphasize that. Maybe I should have. Right. Well, a simply connected domain, let me correct this here. First of all, must be connected. Okay. So this means that if C is a curve in D, then the region bounded inside is also contained in D, but we should say that here somewhere, okay, D is connected. And, okay. So a simply connected domain, by the very wording, must be connected. So this is not simply connected. Since not even connected. Okay. Well, you can also regard a simply connected domain as an open set, a connected open set, but it has no holes inside it, like this. Okay. So, roughly speaking, okay, D must not have any holes. This hole can even be just one point. It's still not simply connected. Okay, now let us see some examples. Okay, we want to evaluate this integral where, okay, C is, say, right, the unit circle. Okay. Counterclockwise orient. Well, here, the first thing we observe is that C is, okay, a closed curve. So when we have a closed curve, we should immediately think of applying Green's theorem because it can simplify matters extremely. Okay. So here, can we use Green's theorem here? Namely, clearly, C is closed. Okay. It's counterclockwise oriented. It's a circle, so it's simple. It's not even, not only piecewise smooth, but it's also a smooth curve. So C is okay. This is in Green's theorem. And the functions P of xy, that is minus y cubed, and Q of xy, that is x cubed, okay, have continuous partials in D, which is all of R2, which certainly is simply connected. I mean, in the plane, you don't have any holes left. So it is simply connected. So these two conditions say that Green's theorem can be applied. So let us apply Green's theorem. Integral over C, now we know C is a closed curve, minus y cubed dx plus x cubed dy is the double integral over D. Now, D here, not D, say R here is the inside part of the unit circle, so it's a unit disk. Okay? Of Q sub x minus P sub y dA, which here becomes, okay, Q sub x would be 3x squared minus P sub y would be minus 3y squared dA over R. Well, if we want to evaluate instead of this the double integral, of course, we see that we have 3x squared plus y squared, which is a perfect setting for polars. So, okay, use polars. Now this is 3r squared, r dr d theta. We have a unit circle. So we have 2 pi times 3 r to the 4th over 4. Okay. So the value of the integral is this. Okay. Now, as a second example, I said A, but yes. So I have a B part. Sorry. So now the same question as above. Okay. Same as above. Okay. But C is the left half of the unit circle. Say, again, counterclockwise oriented. Now, what do we have here? Firstly, our C is not closed. So we cannot apply, okay, Green's theorem. First, C must be closed. Okay, second thing, the function PQ that we want to evaluate is already evaluated over here, okay, in a very nice, simple way, because we can use double integrals and polar here, okay. Well, in that sense, okay, we can still go on our calculations on the same path. We could, of course, directly evaluate it, but we want to use Green's theorem. So, to use Green's theorem, okay, we, for example, complete C to a closed curve. So, complete C to a closed curve. Well, we can do it in many ways. Okay. For example, this being the curve in question, counterclockwise oriented. This is our C. Okay. Now, if we complete it by putting the right half, we would, of course, get the above result. But to calculate C, we would need to calculate the integral on the right side, which is almost the same as this one. So completing this to a closed curve, okay, maybe logical way is to use a straight C1. Then, of course, okay, C total, which is C1 plus C, is closed. Okay, the other conditions are still valid. It's piecewisely smooth now. It has two pieces, two smooth pieces. It's counterclockwise oriented, and everything is fine, and so on. PQ are the same functions, so they have continuous partials everywhere. So apply Green's theorem to CT. This says that integral over CT of P dx plus Q dy, okay, is integral over C1 plus integral over C. Now, this is what we want. So we have to calculate the other two. But in here, okay, because that is a closed curve and the conditions are satisfied, this is double integral over R of Q sub x minus P sub y dA. Well, here R is the inside part. So it's different from part A, but still, okay, it's half of the circle over there. So integral R Q sub x minus P sub y is still, okay, 3x squared plus y squared dA over R. So using polars again, it becomes 3r squared, okay, r dr d theta. R changes clearly from 0 to 1. It's still the unit circle, okay, but the angle changed from pi over 2 up to 3 pi over 2. This time, okay, not 0 to 2 pi, okay. But this is still a very easy calculation. We have 3r to the fourth over 4 times 3 pi over 2 minus pi over 2, which is pi. Okay. So we get half of what we expected. Well, to calculate this unknown, we need to calculate integral on C1 of minus y cubed dx plus x cubed dy. Well, C1 is just a straight line, so we can very easily calculate that. Formulation for C1, parametrization, would be, of course, in terms of y's. Because x is always 0, y changes from minus 1 to 1. So using this parametrization, okay, we end up with minus 1 to 1. Now, y is y, but dx, because x is constant, 0, plus x cubed is 0, we have dy, so it is 0. Okay. Conclusion. Okay. The integral over c of p dx plus q dy, from our formulation, it's the double integral over r, where r is half circle, minus integral over c1, but this is 0, and this is, as we calculated over there, 3 over 4 pi. So the result is 3 over 4 pi. So using Green's theorem can simplify calculations. Now this will be more precise in the following examples. Now this time, let us consider the following example. We have integral over c of y squared dx plus 2xy dy, and c, in the first case, c is given by the following. At minus 1, we have a straight line. Up to 1, we have straight lines. By the way, this is level 2, and this is 1. So here we have a half circle. Okay, this is a circle. So counterclockwise oriented, fine. So before we compute anything from here, we see that, okay, we have polynomials, so they have continuous partials everywhere, hence in R2, which is a simply connected domain, nice enough. And inside C, they also have continuous partials. On the other hand, C satisfies the conditions of Green's theorem. That is, it consists of 4 pieces, each of which is smooth. It's closed. It's simple, counterclockwise oriented. So, okay, we see that C and P and Q satisfy conditions or hypotheses of Green's theorem. So applied. So applying Green's theorem means we calculated Q sub x minus P sub y. Well, this is Q, this is P. So we have 2y minus 2y, which is 0. So we have integral over C is integral over R of 0, which is 0. So we are finished. We don't have to calculate anything else here. Now, as in part B, I will use roughly the same setup, but this time okay, the curve will be this one. Again, 2 and 1 and 2 here, etc. Now, what does all this say? Well, C is a curve which starts from minus 1, 0, to, okay, minus 1, 2, following this path. Okay. Well, but we know something about our function. Namely, okay, that's the first thing you should check all the time. So firstly, we check, okay, if Q sub x is P sub y. Well, we already did it in part A, okay, which is okay. From part A. Well, this says, of course, because we have a simply connected domain, it says that our function is conservative. Okay. So, since D is R2 in this case, is simply connected, okay, PQ is conservative. Because these were equivalent if we had a simply connected domain. Well, because we have a conservative function, okay, it means that, so, okay, the integral p dx plus q dy is path independent. Indeed, which means everywhere. So this is a path-independent integral, and we want to evaluate it from this point, call it A, to this point, which is B. Well, why should we calculate it over this difficult curve, which is in 3 pieces? Okay, so choose an easier path, a simpler path. From A, that is minus 1, 0, to B, which is 2, 0. Sorry, minus 1, 2. Okay, why is 2 here? Well, a very easy curve which goes from A to B is a straight line. So, okay, the integral over C, the given one, is the same as the integral over C1, where C1 is going from this point up to this point straight. Okay, from minus 1 to the level 2. Well, it's very easy to calculate our integral now. This is, well, a formulation would be, of course, maybe I should write that here. Okay, y is the variable because x is constant and minus 1 here. And y changed from minus 0 to 2. Well, let us look at our function values. We have y squared. That's good. Y is y. And dx. Well, x is constant and minus 1, so it is 0. Plus, we have 2xy. Well, x is minus 1. Okay? And dy from 0 to 2. So the whole integral is actually minus 2y dy, which happens to be minus y squared, 0 to 2, so it is minus 4. Okay, x is right, minus 1. Y is from 0 to 2, so we end up exactly at this point, minus 4. So, looking at whether q sub x is p sub y, even though the region is not simply connected, can pay. Okay, the benefit. So, it's always a good idea to check this all the time. Okay. Well, a slightly different version of this is the following. we want to calculate the integral over C of y squared plus x dx plus e to the y 2xy dy, and C is as in and C is as in 2a, that is, let me redraw it. C is this. This was -1, this was 2, this was 1, and this was a circle and counterclockwise oriented. Okay, as in 2a. Right, so we want to evaluate this integral over these 4 pieces. Well, this is quite a lot of work. Certainly, we don't want to do it. You can formulate the solution by calculating the 4 curves and their parametrizations, do it in 4 integrals, but still you have lots of very strange functions. And Green's theorem tells us that most of them are just don't play any role in the value of the integral. Why? Well, because q sub x, okay, would be just 2y, and p sub y would be 2y. Okay. Well, all this says that, let me check this. I can change this a little bit though. Right, maybe I should next time. So this tells me that the derivative with respect to x would be 2y here. The derivative with respect to y here would be 2y. They are equal. And these are 2, okay, simply connected. So this means that, okay, we have an exact differential, or that this is conservative. Okay. Thus, by Green's theorem, integral C p dx plus q dy, which is double integral of q sub x minus p sub y, which is 0, is 0, and we are finished. Okay. Well, suppose we had the following version, the same as, okay, 3, but we have the following. We have y squared plus x plus y now, dx plus e to the y plus 2xy dy. Now, C is the same, so it's a nice counterclockwise oriented, piecewise smooth, simple closed curve, as in Green's theorem, and our P and Q satisfy the following. Q sub x would be 2y, P sub y should be 2y plus 1. Now, this tells me that this is not an exact differential. That is, it's not conservative. Okay. So, PQ is not conservative. This was a necessary condition, that's this should be equal, was a necessary condition to be conservative. But, okay, for this equality to imply conservativeness, we needed a simply connected domain. We have a simply connected domain here, but these are not equal, so it's not conservative from the start. So what should we do? Start all over again. by parameterizing and so on. Of course not. Okay, we use what we did in 3. In other words, okay, our integral in this example is the integral of, okay, y squared plus x dx plus e to the y to xy dy plus the integral of y dx. Namely, I separated this one because I know this is 0 by 3. So I only have to evaluate this part, which is quite simple. Well, one has to work very shortly. And you can see that it is not difficult at all. Maybe we should calculate that. If you are practical enough, you will see that it's not a big deal. So we have to calculate integral c of y dx. Okay. Well, let us go back to our curve again. Okay. It consists of 4 pieces. Let us start with C1. We have y dx. Well, on C1, from here up to here, clearly y is 0. So it is 0. Okay. Integral over C3. Okay. C2 is the most difficult one. Not difficult, but relatively more difficult. So I will continue with C3. Of course, this is 1 and this is minus 1. So I have y dx. Well, the parameterization for C3, of course, is x2, where x changes from, okay, 1 to minus 1. Well, that's not possible. From minus 1 to 1. So this is minus C3. A parameterization. Okay. We go from minus 1 to 1. That's our x. And y is constant and 2. So this would be the negative of the integral over minus C3, which is minus, now this formulation, okay, from minus 1 to 1. Okay. Y is constant and 2. Dx is dx. Okay. So it is minus 2x. So 1 and minus 1. That gives us minus 4. Right. So integral over C4 y dx. Okay. This would be as before. Okay. Let me directly write it. Maybe not. Okay. So C4 could be formulated as x is constant and minus 1, and only y changes. Y changes from minus 1 to 2. Okay. But this is, when y increases, traced in the opposite direction. So this is actually minus C4. So use this. Minus 1 to 2. Okay. Y is the variable. So we have y. And actually, we didn't need this. Anyway. So we have dx. Now, x is constant and 1. So this is 0. So that would be 0. And finally, we have C2. Y dx. Well, we have to formulate this and be a little bit serious here. So, for example, C2. What do we have for C2? Well, C2 is a curve. Fine. Okay. And it is not a straight line as in the previous cases. it's a circle, so we have to use a circular parametrization, but it is a shifted circle. Its center is at 1, 1. Okay. So, because its center is at 1, 1, we could use the following characterization. It's a unit circle, so this is cosine t, and y minus 1 is sine t. Well, the sum of the squares is 1, as expected. Okay. Well, this, of course, says that t runs from, well, these shifts brought the center to the origin. So, okay, so the angle changed from minus pi over 2 to pi over 2, because if we look at this half circle here, okay, it is at the center, and so the angle changed minus pi over 2 to pi over 2. And it, when t increases, it has this correct direction with counterclockwise direction. Well, so this says we have y, which is 1 plus sine t, and we have dx, which is minus sine t, dt from minus pi over 2 to pi over 2. Okay. Well, integrating, am I correct? I have minus sine t, yes. So we have minus sine t, integral would be cosine. At these points, it is 0. So this is the same as just the integral minus pi over 2 to pi over 2 of minus sine squared t dt, and this being what? Cosine 2t minus 1. So integral over 2. So integral would be 1 over 4 sine 2t from minus pi over 2 to pi over 2, which would give me 0 again. Okay. So all in all, the value is minus 4 again. Okay. Well, a similar question, which was, I think, asked in some exam with some humor in it. That was my third question, so this would be 4. Okay. The question is to evaluate e to the x plus y squared dx plus 2xy plus sine y dy, where c is the following curve. Starts from here, okay, goes as follows. And comes to this point. Well, the first thing we observe about this picture is that this is actually, except for the endpoints, of course, it is a smooth curve in the first place. It's a simple curve, all right. Okay. It's not closed. The orientation is this one. So we cannot use Green's theorem. But, of course, when we look at P and Q's, which is, as I said, the first thing you should check, Q sub x would be just 2y, and P sub y, okay, when you look at it, is 2y, so they're equal. Well, that's good news. Well, all functions have continuous partials everywhere, so we can take D as our plane, R2. So, okay, so this is true on R2, which is simply connected. It has no holes in it. So, PQ is exact. I mean, okay, I always use the math terminology, is conservative. Okay. It's conservative. So, okay, it has a potential, and we could find the potential, put 1 in it, and then 0, these points. Actually, I mean, you don't put 1, 0, of course. You put 0, 1, and 0, 0. And then this would give us the value, but we don't have to find the potential. Okay. Well, we could use path independence. Now, we know it's conservative. So, okay, use path independence. Okay. Since PQ is conservative, okay, P dx plus Q dy is path independent. So, all we have to worry about is how we go from 0, 0 to the point 0, 1. Well, of course, this is a nice path. Maybe it may have a meaning, which is very mysterious, but, okay, an easier path clearly is this one. Okay. So, going from 0, 0 to 0, 1, I don't have to use the given path. Instead, I can use this one, okay, namely integral over C is integral over C1 by path independence. So integral C would be the integral. Formulation, of course, is very easy for C1, namely we have obviously x identically 0, we have y, and y changes from 0 to 1. This is C1. So using it, 0 to 1. Now let us look at inside. Okay, x is constant and 0 all the time. So this is 1 plus y squared. Y is y. And we have dx. But x is constant and 0. So dx becomes 0. 2xy, well, x is 0. And sine y and dy. So the whole integral is nothing but 0 to 1 sine y dy, which would be minus cosine y. So that would be 1 minus cosine 1 at the end. Okay. So if we are careful about our function, this may happen to be quite easy.